Let's come to something a little bit more complex, but without much explanation. It's a process called coastal upwelling, and it is driven by winds which blow along the coast. You need the Coriolis force to stimulate upwelling, and you need the right orientation of the wind. And this is shown here in a simulation of several days in duration, and in the first part of the simulation the wind is in the right direction, and then the wind direction is reversed, which actually creates something that's called coastal downwelling. But anyway, let's have a look at the model domain. You look from the side. It's a 2.5 dimensional model. It has a sloping seafloor, and it has essentially a two-layer setup where you have low density light water sitting near the surface, something like 20 meters deep, surface mix layer. Then you have a density jump, a change of the density, and then you have a slightly stratified lower layer. And then you start the simulation, then you can look at the dynamic and learn about code. And this, for example, is the result of coastal upwelling. After you run it for, this is shown here after 3 days, the top image shows you how the density field looks. And upwelling is the movement of near bottom water into the surface layer. You can see here near the coast, I forgot to mention that we have a coastline. You can see the blue water ends up near the surface. And you can also look at the horizontal flow fields. You get offshore movement near the surface, onshore near the seafloor. These are Ekman layers. And you get actually a very strong swift flow which runs into the page as an upwelling jet. Something like, how much does it have here? 60 centimeters. Okay? And you learn more about that mechanism. You can read it up the deep. But this is what you can also simulate with the 2.5 dimensional. Sounds weird, but I mean, this is, just to remember is we assume that all variables have no gradients in or out of the model domain, but you can still simulate currents perpendicular to the model domain.